Question 7. The matrix M is given by 3, 0, 2, 1. Show that M to the 4 is that. Right, so that's a nice start. We can do that. Part 1. Well, we need to get M squared first, don't we? So if M is 3, 0, 2, 1, M squared is 3, 0, 2, 1 times 3, 0, 2, 1. And we know how we multiply 2 by 2 matrices. That's 3 times 3 plus 0 times 2. 3 times 0 plus 0 times 1. 2 times 3 plus 1 times 2. That's 6 plus 2, that's 8. And 2 times 0 plus 1 times 1. So we get that 9, 0, and other stuff. 8, 1. Now, we're not going to multiply that by 3, 0, 2, 1, are we? Because that, you know, we've got to get there as quickly as we can. M to the 4 is M squared times M squared. And that will save us a little bit of time rather than working all the way up there. Depending on how pushed we are for time, we could just write the answer down. But yeah, we'll do it. 81 plus other stuff. You know, what are we doing? Yeah, 0. 81. 9 times 0 there, that's it. 9 times 8, 72 plus 8 is 80. Blah, blah, blah. There we go. Right. Great.
Dave, if say we were trying to find M to the 3, and we had to times 9, 0, 1 to 3, 0, 2, 1, which side of the 9, 0, 8, 1 would the 3 1 go? Would you times it back? Would you put M then M squared, or
in this case, it would be either. Both would give us M cubed.
Okay.
They would both give us the same answer.
Nice.
Now, hence suggest a suitable form for the matrix M to the n, where n is a positive integer. Right. So we've taken 3, 0, 2, 1. So that is. Let's just remember what we've done here. That is 3, 0, 2, 1. To the power of 4. Now how can we make a connection between that and that? Well, 3 to the power of 4 is 81, isn't it? 3 squared is 9. So that seems to fit, doesn't it? And this is 1 less than 9, and this is 1 less than 81. So I think our suitable form is going to be m to the n, was it lowercase or uppercase? Lowercase. Is 3 to the n, that gives us the 81 and the 9, and this must be 3 to the n, take away 1, and then these are going to stick at being 0 and 1. That's my suitable form. That was only 1 mark, wasn't it? 2 marks, oh wow, great. Use induction to prove that your answer to part 2 is correct, and you're in a bit of trouble if your answer to part 2 wasn't. So part 3, use induction to prove this. We're going to start, now remember we just talked about this, we're going to start with n being 1. Let's make sure this works for n equals 1. M to the 1 equals 3. 3 minus 1, 0, 1, which is 3, 0, 2, 1, which equals m as required. Great, so it's true for n equals 1. Good start. Now we're going to state our assumption. Assume true for n equals k. That means that m to the k is 3 to the k, 3 to the k, take away 1, 0, 1. There we go, we've stated our assumption. Now given that, we need to prove that this thing works for k plus 1. And let's think through what we're after here. We would like what would it be? 3 to the k plus 1, 3 to the k plus 1 minus 1, 0, 1. That's what we're after. It's a fairly obvious one that we're looking for in this case, but that's it. you've got to be careful that, don't think that just by writing that that's enough. It's got to be clear that that's just you giving yourself a little pointer to where you're heading. So what we're going to do, we're going to say m to the k plus 1 is what you get if you multiply m to the k by m. Or the other way around, m by m to the k. And m to the k, using our assumption from earlier, is 3 to the k. 3 to the k, take away 1, 0, 1. And this is m to the 1 that we're dealing with here, which was 3, 0, 2, 1. Like that. So we're going to multiply these together, showing all of our working out for this. That gives us 3 to the k times 3. Plus 0 times 2. 3 to the k times 0 plus 0 times 1. 3 to the k minus 1 times 3 plus 1 times 2. Have we done that right? And 3 to the k minus 1 times 0 plus 1 times 1. So that's there. And I'm showing all my working out, and I'm making it really clear that that's where we've got at this point. And now I've got to tidy this up. So just using our core 1 indices stuff, we've got 3 to the k times 3. That's 3 to the k times 3 to the 1. We add the powers. 3 to the k plus 1. The 0 I'm delighted with. That 1 I'm delighted with. Let's work out what's going on down here. Down here we have 3, multiplying out this bracket, we have 3 to the k times 3 to the 1. That's 3 to the k plus 1. Take away 3, plus 2. I may be overstating this, but we're definitely there now, aren't we? That's exactly what we were looking for. That's what we have to establish as our result. Okay, nearly there. Our statement, to finish this off, so if for n equals k, then also true for n equals k by n equals k plus 1. As it is true for n equals 1 by mathematical induction, m to the k equals 3 to the k 0, 3 to the k minus 1, 1 for all, I've just used k in there, but I should have used n, shouldn't I? Oh, look at that. Great editing, Dave. Oh. That's an n. For all integer n greater than or equal to 1. There we go. Are we happy with that? And that's maths.